Okay, let's do problem number 49 on page 172. I'll read the problem. A 615 kilogram racing car completes one lap in 14.3 seconds around a circular track with a radius of 50 meters. The car moves at a constant speed. What is the acceleration of the car? And what force must the track exert on the tires to produce this acceleration? So, given. So we got a circular track. Now I like to try to show the car going around the path because I want to draw the forces acting on the car. So I'm going to do this. Now you go, that's not a circle, but we're looking at it edge on. Okay, it's kind of an oblique view. And I like to draw the car right here. So here's the car, and it's just going every 14 seconds or so it goes around the turn. And the mass of the car is given to be 615 kilograms. Okay, the speed of the car, V, is constant. So it's going around a circle, constant speed. Now, does that mean the velocity is constant? Is the velocity constant? Well, the speed is constant, but the velocity isn't, because velocity includes direction, and the direction is constantly changing. And that's why you need an acceleration. You need an acceleration to change the direction of your velocity vector.
Well, you just wrote V is constant.
V without the vector head on it. Constant speed. Changing direction. Now we call this uniform circular motion. It's driving in a circle at a constant speed. And then and the radius is 50 meters. So we'll just say R equals 50 meters. And you can use capital R, lowercase r, whatever you want. And what are we trying to find? What is the acceleration? And B, what force is applied to the car? What force must the track exert on the tires to produce this acceleration? Now that's really the force of friction. So what's the force of friction acting on the tires of this car? So let's solve it. Now we want to find the acceleration. If you have a car that's in uniform circular motion like this, you can say, well, the acceleration is going to be equal to v squared over r. That's the magnitude of it, and the direction is pointed towards the center of the circle. But we don't know what the velocity is, do we? Oh, one thing I forgot to mention. How long does it take to go around? I forgot to put that on here. We call that the period. So the time it takes to make one lap, that was given to be 14.3 seconds. Okay, so this tells me, look, do I know what the radius is? Yes. Do I know what the velocity is? No. But I can figure it out. Because I know the radius of the circle, I can figure out what distance you go when you make one lap. And I know the time to make one lap. So distance over time is my speed. So V is equal to 2 pi r. That's the distance around a circle, isn't it? 2 pi r? Divided by the time it takes to go around once. Hey, this should be on your equation list. Speed equals 2 pi r over t. Now, you have to know, if you're going to put that on your equation list, you better know what the assumption is. The assumption is we're going around a circle. And that this is the radius of that circle, and this is the time it takes to go around that circle once. It only applies to that situation. So what is that? That's 2 pi times 50 meters divided by the period, which is 14.3 seconds. So where's my calculator? Let's see. Turn it on. So I go 2 times pi. Where's my pi button on this calculator? Oh, I'll just go 2 times 3.14159. That's more than enough. Times 50 divided by 14.3. And I get 21.96. I'll just write 21.97. Yeah, geez. So now the acceleration, now that I know this, is just going to be 21.97 meters per second. You got to square that. And then divide that by r, which is 50 meters. So I'll take that answer and square it. And then I'm going to divide that by 50. And I get 9.65. meters per second squared. And that's yeah, the book got 9.68, but I think that's just rounding off differences, so that's good enough. Now that's my centripetal acceleration. Now the book did it a little bit differently, or if you want, you can do it. We have this equation for circular motion, and what you can do is square this and plug it in here and derive another equation. So you can say A equals V squared, but that's 2 pi r over the period. Square that and divide that by, well, I'll just use little r. Divide that by r, and then you get, okay, A equals, well, that's 2 squared is 4, pi squared, r squared over the period squared divided by r. So this r cancels with that, and so you get this equation, 4 pi squared r over the period squared. So based on what's given, now this equation was in your book, and I saw a lot of you using it, which is fine. But this is the centripetal acceleration if you're given the radius and the period. And that's fine, you can do that. If you did that on a test, I'd be perfectly happy. But I don't know, I prefer to actually figure out what the speed is and then plug that into v squared over r. Either way, you're going to get 100%. Any questions on that? Okay, so that's all for part A. For part B, we want to know, what is that force of friction? Well, let me draw a free body diagram of the car. So here's the car, here's the tires, here's the windshield, or what, it's a terrible car. But it's going around a circle, you know, like this, all right. But this is the ground. And maybe it's coming right at us or going directly away from us. But anyway, we've got gravity, right? And then we've got normal force. Now, where is the normal force applied on a car? To the tires. You got 4 tires on a typical car. I'm just going to show it as 1 normal force. And then when you go around turn, what's the force? What is the agent that's actually causing the acceleration? Because these two are going to cancel each other out. There's my force of friction. And that's what causes the centripetal acceleration. Now what I always do when I deal with a problem like this, I make this the x direction and this the y direction. And if I sum the forces in the x direction, I get ma in the x direction. Well, I already know what a is. It's 9.65 meters per second squared. So, and there's only one force, that's the force of friction. The force of friction will be equal to M, which is 615 kilograms, times A, which is 9.65 meters per second squared. And you get 5,934. I'm just going to round it off to 5,900 newtons. So that's the force of friction acting on your car that's making you go in a circle. That's a pretty big force. It's a big car. It's moving fast. It's going around in a circle. You're going to need a lot of force to do that. And, yeah. What did I get? Yeah, they kept another digit. That's okay. Any questions on number 49?
The only force in the x direction is friction.
Yeah. And now, you know, unless somebody is pulling on it with a string or something, yeah. And notice, I didn't call this the centripetal force. I called it the force of friction on the free body diagram. You never want to label something as a centripetal force on a free body diagram, because the centripetal force is the result of all the forces acting on the object. So you want to draw those, the force of everything acting on the object on your free body diagram, and then if the net force turns out to be a centripetal force, well, that's fine. Okay. So, big picture here. If something's moving with constant speed around a circle, the acceleration is called a centripetal acceleration. It's equal to v squared over r. If all they give you is the radius and the time it takes to go around once, you can figure out the velocity, the circumference of the circle divided by the period. Or you can make a substitution and use this equation to figure out what the centripetal acceleration is. Well, if you have a centripetal acceleration, you need a centripetal force. That force, it would be the net force. So net force is mass times acceleration. What causes that net force in this problem? The force of friction. So if you're walking around in a circle, it's the friction between your feet and the floor that's causing that centripetal force. Or if you're going around a turn in your car, it's the friction between your tires and the road that's causing that centripetal force that's causing your centripetal acceleration. That is all.